So I didn't do anything off-stream. I'm probably gonna keep it that way because I want to reserve my off-stream time to build other stuff like personal projects. So I'm just going to... I'm gonna try to build the... I'm gonna try to follow here, this plan here, instead of researching. So I'm gonna try to build level sensitive latch. Then if I sense that is not working, then I'm gonna use ChatGPT to search a better way. So starting from something real. Gonna read the last response from the threads I opened.
They contain no memory. They do not care. Good, now we can ground this completely. I'll be explicit and prescriptive. No philosophy, no meta. I'm going to answer exactly what you asked. But the first level actually is whether it has inputs, outputs, what gates to use, how you know it's correct, how this sets up phase 1 and later work, how to test things in Component Factory without the game's test harness. First, stop thinking in levels. In Component Factory, you are not solving levels. You are manufacturing primitives. So the question is not, did I pass? It is, does this component obey its contract under all legal uses? That's the only correctness notion that scales. Yes. Does this component need a clock? No. A latch is level sensitive, not edge triggered. How you test it, this is important. You do manual temporal testing, not exhaustive input testing. Test protocol. Set in equal to 1. Toggle D. Q must follow immediately. Set on equal to 0. Toggle D. Q must not change. Toggle N equal to 1. Q must immediately update to current D. If this holds, the component is correct. If not, it is wrong. That's it. No counters. No clocks. No sandbox yet. What you name it. Name it something explicit like latchon, byte level. This matters later. Component 0.2, edge-triggered flip-flop, master-slave. Only after 0.1 works. Inputs. D. LK. Internal structure, mandatory. You must instantiate 2 copies of latchon byte level. Master latch. On equal to CLK. Slave latch. In equal to not GLK. D. Master, slave, Q. This is not negotiable. Do not improvise. Required behavior. While TLK equal to 1. Master follows D. Slave is closed. When CLK transitions 1, 0. Slave captures master. Q changes only on the falling edge. This is now an edge-defined state element. How you test it. Manual again. Hold CLK equal to 1. If Q ever responds,
skip some of this.
Why this matters. This gives you a single global notion of time. How you test any future component, general rule. From now on, every component falls into one of 2 classes. Final answer to your... If you do only this next, do not jump ahead. But phase 0 must be mechanically complete first.
So what I was thinking about for this level sensitive latch, I never saw this one. I saw the SR latch, master slave latch, and D flip-flops. They're all variations of the same pattern, but I'm not really sure like which one to build. So like on the step obviously it says this one that I don't know what it is. And based on ChatGPT descriptions, I was thinking about this AND gate. But the thing that I'm not really sure about is it's supposed to be like this cycle between combinational logic and memory. I'm not really sure how to do this if I can do it on Turing Complete or not. Yeah, so this diagram here basically. And so there's 2 things that are kind of unclear is what the combinational logic should be. It's kind of abstract. And the other one is obviously whether or not I can do this on Turing Complete with this loop here with the memory. But just based on the simplest uh, thing there, the description, I think that's. But this is obviously not gonna work. So I'm not really sure, because if I put the output of the memory here, it doesn't work. So obviously the AND gate is the one for like only allowing this input to pass if the other one is available. But I know that the SR latch and I think the SR latch, there are two variations, one with NAND gates, I think two NAND gates, and the other one with NOR gates. But it's basically the same pattern, it's like a toroidal thing. But I think I'm gonna do this on another one, on a separate custom component factory. This is basically this pattern here. So I'm gonna ask that to GPT to clarify. Actually, no, if I can put them on the same thing. So it does use an AND. ChatGPT a lot of times use this Q here. I don't understand why it does that. But maybe in this case, supposed to be the output. In other situations is not really the output. And obviously, sometimes it hallucinates. So it's kind of annoying, but then you just iterate and try to clarify, figure out. The saying that I should have the enable, and one of the inputs is going to be the. I'm considering the top input is as the enable. So this is going to have a not here as well. So not. Then another ends. Here. So it's saying to put the output here. I don't think this is gonna work. That is the problem. I'm not sure what it means as well by this queue here. I guess I could use like a delay line here or something like this, but I also think it's not gonna work as it should work probably. Let's see, when it's on here, when the enable is on, then it's gonna capture the input here. It's gonna start here. And then when it's off, it's gonna be on, and it's gonna be on. And just, I think the cycle is just to maintain the value in case you sat. Let's see what it means by the queue there.
Good. Now we lock this down mechanically and remove all ambiguity. You are building one specific thing. A level-sensitive 1-bit latch. With inputs D, N, and output Q. I'll give you two valid constructions. The canonical gate-level latch, conceptual ground truth. The Turing-complete practical latch, using the 1-bit memory gate. You should understand both, but you may implement, two, to proceed. What a level-sensitive latch is, precisely. A latch implements this recurrence. In a copy code Qnext equal to ND in Kuprev. Interpretation. When n equal to 1, Qnext equal to D. When n equal to 0, Qnext equal to Kuprev, state is held. This equation already tells you. You need and. You need not. You need or. And alone is insufficient. Holding state requires feedback. 2. Canonical gate-level latch, conceptual reference. This is the real schematic independent of Turing-complete limitations. Signals. This is the latch. There is nothing missing. The loop is simply scopy codec Q, and 2, or 1, Q. 3. Why this is hard in Turing-complete. Turing-complete forbids pure combinational loops because the simulator can't resolve them. Real hardware relies on analog delay, TC does not. So if you try to literally wire this with gates, TC will block you. This is expected, not a mistake. 4. Correct solution in Turing. Complete, use the 1-bit memory gate. The built-in 1-bit memory gate already is a latch, FF primitive. It exists precisely to represent storage without illegal combinational loops. You are allowed to use it here to anchor semantics. 5. How to build the latch using the 1-bit memory gate. Memory gate interface as you described. Savine. Save all. Out. We want. When n equal to 1, write D. When n equal to 0, hold previous value. That maps exactly. Wiring. This is the actual build.
That's
Scopy
basically,
coded. Folded. Saval. N.
I think it's saying is basically this sensitive level is already this 1-bit memory here. And I think you get this from the levels there on the campaign. Also, the other thing that I realized is when you hover here, you can see on the top left, you can see the name of the level. And I saw a video where the guy had like the description here. I wish they had this by default. And I'm not really sure how to put this. But it doesn't matter that much. So these are the levels here related to memory. So I think that this is 1 byte. So maybe it's before this one. The bus. I think this is probably that component. So this circuit here creates that 1-bit memory, I think. Yeah, and this is a NOT and a switch. Yeah, so it's exactly what it's saying there, basically. Pretty much the same, but it's using the switch, which is also comes from another level that I don't remember which one it is. But it's probably gonna be those primitive gates that is said there. Is the AND, the OR, and the NOT. So let's see. So when this is on, it's supposed to save, to allow saving the value. So this is gonna be off. This is gonna be on. So it's gonna pass whatever value it has here. This delays one line, but I don't understand why. I think what I'm gonna do is saving gracefully. I'm gonna see if I can go back to the switch. Oh, this already has. I'm gonna finish reading the response from ChatGPT. Then I'm gonna go back to that level, and I'm gonna write down the gate to ChatGPT, the schematics, and ask it to explain why does it work that way, and whether or not that's a level sensitive latch. Because if it is, then I'm not gonna do it on the custom component factory that I have there. I'm just going to rename to the next level. Because I'm pretty sure on this here, they don't allow you to build the normal SR latch. I think I'm gonna do that on the custom component factory. It switch. Yeah, so this one is the switch that you get on the other level, I think. But this already has a. So these builds, I think there are two types of switches. I think this one is a 1 bit, and the other one is for like bytes as well. But I'm not really sure if this. Because the level is bit switch, so it should be 1 bit, but it already offers the switcher, which is kind of weird. Yeah, I'm not really sure where you get this. You guys can look into the dependencies here. That should come from this and this. I don't think that's there is a good. I wish they had the same stuff that they have for the custom components, where you can click to see where it goes, where it comes from, on the built-in gates as well. Because now I'm not really sure where does it come from. Yeah, I don't think that there's gonna be a clear level where it builds the switch there. Let me finish reading this.
N. What? N. What? Savvy. This is the latch. There is nothing missing. The loop is simply copy codec, and 2 or 1. Free. Why this is hard in Turing complete. Turing complete forbids pure combinational loops because the simulator can't resolve them. Real hardware relies on analog delay, TC does not. So if you try to literally wire this with gates, TC will block you. This is expected, not a mistake. 4. Correct solution. In Turing complete, use the 1-bit memory gate. The built-in 1-bit memory gate already is a latch FF primitive. It exists precisely to represent storage without illegal combinational loops. You are allowed to use it here to anchor semantics. 5. How to build the latch using the 1-bit memory gate. Memory gate interface, as you described. Savine. Save all. Out. 6. Why this is not cheating. Conceptually, The memory gate embodies the feedback loop plus storage delay. You are using it to represent physical state. Later, you will wrap this inside higher-level timing discipline. You are not skipping understanding. You already derived the equation. 7. How to test it, step by step, no hand-waving. Do exactly this. Initial state. N equal to 0. Equal to 0. Observe Q, whatever it is. Test 1, transparency. Set on equal to 1. Toggle D between 0 and 1. Q must track D immediately. Test 2, hold. Set N equal to 0. Toggle. Q must not change. Test 3, recapture. Leave D at some value. Set on equal to 1. Q must update to D. If all 3 pass, the latch is correct. If any fail, it is wrong. There are no other tests. 8. What not to do, common traps. Do not. Add a clock. Add counters. Try to make it tick. Expect this component to be meaningful alone. This component is foundational, not functional. 9. Where to get real schematics like this, gate level, not pictures. You want logic equations and transistor level intent, not block diagrams. Best sources. Computer Organization and Design, Patterson and Hennessy. Latch, FF equations are explicit. CMO's VLSI Design, Westy and Harris. Canonical Latch, FF implementations. Shows why feedback is required. MIT 6, 0046. 191 lecture notes. Clean gate level schematics. Explicitly discusses transparency versus edge. Open source HDL cores, read the RTL. For example, simple Verilog latch. Verilogcopy codeaways, if, in, Q equal to D. This is the equation you implemented. Avoid. Blog posts with cartoons. Clocked box diagrams. FPGA tutorials that hide semantics. 10. What this unlocks next. Once this latch exists, you can build master-slave FF. You can define when state is allowed to change. Arithmetic phase 1 becomes clean and clock-free. Debugging stops being mystical. You are doing the right first thing. If you want next, we proceed immediately to building the master-slave flip-flop using this exact latch twice. That's where time finally becomes concrete.
So after this explanation, I'm going to move on to the second and third, I think. This edge triggered flip-flop. I'm probably gonna build the. I'm gonna ask this as well. I'm not really sure like how much I should compose the gates. Because one way to do this would be to build the SR latch on a separate component factory, which I think I'm gonna do it anyway. So I'm gonna do both the NAND and the NOR version of the SR latch on their own custom component factory. But then I could either build this like on its own without using other components, or I could use the SR latch to build this one. But I think I'm gonna have to build it on its own because it involves creating other wire that connects the logic gates that are parts of the SR latch. So it's probably better to not compose. Yeah, I'm not gonna ask. I'm just gonna build like separately. So build the SR latch versions first, then build this master slave. So in master, or maybe actually not. Maybe I can do it. Maybe I can compose. Maybe it's better to ask. Because from what I remember, master slave is just two SR latches connected together, where one determines what happens on the other, I think. Then you have the other variation, it's going to be the flip-flop, I think, which instead of manually setting the value, you set it based on the clock cycle, I think. The clock cycle and a control wire. So it basically allows you to pass data from one part of the system to the memory based on the clock cycle. Then obviously this probe here as well is kind of confusing. I'm gonna see if I can try to use this to try to understand how it works, but I think it's something you use for debugging but I don't know how it works very well on the custom factory there.
Conceptually, the 1-bit memory gate you already have is a level-sensitive latch. What that campaign level, saving gracefully, made you build, is exactly the same storage primitive, just spelled out with switches and a delay element instead of being packaged as a single gate. Let me unpack why that circuit works, step by step, in causal terms. What the circuit is trying to implement. The semantic target is the latch equation. Nothing more, nothing less. So the circuit must satisfy two requirements. Transparency, when n equal to 1, output follows input. Retention, when n equal to 0, output feeds back into itself. Everything in the schematic exists only to enforce those two facts under discrete simulation rules. 2. Identify the roles of the parts you describe.
I think I understand how it works here. It's kind of confusing because this output here is directly connected to here. So maybe I could do like this, and it would be the same. Might make it less confusing. But it's basically when both of them are turned on, then it's gonna be. So this is the enable. So when this is turned on, it allows the whatever value you have here to pass, which is gonna set this delay one. And this is gonna wait for the next tick to set the value of the outputs. And because it's connected here, the NOT gate is only gonna is not gonna change the value if the enable is 0. So it basically creates a loop here. I think that's how it works. Not that hard to understand.
Described. From your description, the circuit has input data switch. This is D. Enable switch. This is N. Not gate on N, produces N. 2 switch components. These are conditional pass elements. Delay line. Feedback wire. Each element corresponds to one term in the latch equation. 3. Rewrite the schematic in logical roles. Let's rename things abstractly. Switch A, data path, active when n equal to 1. Switch B, feedback path, active when n equal to 0. Delay line, enforces temporal separation so feedback is well defined. Output node Q. So structurally. Copy code, D, switch A, Q, delay, switch B. N controlled. Feedback path. Where? Switch A is enabled by N. Switch B is enabled by.
Maybe I'm not really sure if I understand why I can't connect directly there. I think it should prevent like overriding, but it's kind of confusing to think about. As this should prevent circular dependency. Yeah, because if it flows there, then it flows here as well on the entry point. I think that's probably why it has to be like this. So it should make sure that when you're setting, the signal doesn't overflow on the 2 switches, I think. Doesn't go back.
N. 4. Case analysis, why it works. Case 1, n equal to 1, latch is transparent. Switch A is on. Switch B is off. The feedback path is cut. Q is driven directly by D. Delay line is irrelevant because feedback is disabled. So, in a copy codec equal to D. Exactly what we want. Case 2, n equal to 0, latch is holding. Switch A is off. Switch B is on. Input D is disconnected. Output Q feeds back through the delay line into. This is 5. Why the delay line is not a hack. This is the key conceptual point. In real. 7. Why the built-in 1-bit memory gate is the same thing. 8. Why this matters for what comes next. This understanding is exactly what you need for master-slave flip-flops, 2 latches plus complementary enables, pipeline registers, hazard reasoning. Why combinational loops are illegal, but sequential loops are not. You now have the missing causal picture. State is feedback plus delay, nothing else. Everything higher level is composition. At this point, you are justified in treating the 1-bit memory gate as a latch primitive, and moving on to the master-slave FF, because you now know what it is doing, not just how to place it. If you want, next we can walk through building the master-slave FF purely in terms of this latch, or formalizing how this same idea scales to registers and pipelines. But conceptually, You've now closed the loop that was confusing you.
I think edge triggered is already based on the clock cycle.
Short answer first, then the reasoning. No, you do not need to build SR latches, nor a NAND to proceed. Yes, building them once is pedagogically fine, but they are not load-bearing for the rest of your project. The minimal sufficient phase 0 set is smaller than what you're proposing. Now, the precise structure. What role SR latches actually play? An SR latch is not a distinct capability. It is a historical construction of a bistable, with asymmetric semantics, illegal states, that real systems almost never expose architecturally. Nor SR latch equation. Make full copy codec equal to R plus Q equal to S plus Q. NAND SR latch equation. Make full copy codec equal to SQ. Q equal to RQ. What they demonstrate. Feedback creates state. Mutual exclusion matters. Invalid states exist if control is underspecified. What they do not give you. A usable write enable abstraction. Clean timing semantics. Safe composition guarantees. That's why modern design almost never uses SR latches directly, they are teaching artifacts. 2. The latch you already built subsumes SR latches. Your level-sensitive D latch with enable already strictly generalizes SR. Equal to ND. R equal to ND. This mapping removes the illegal sequel to equal tune case by construction. So architecturally, SR latch D latch with enable. Once you have a D latch, SR latches add no new expressive power. 3. What phase 0 actually needs, minimal sufficient set. To support everything in later phases, pipelines, UO, caches, IO, DSP, you need exactly 4 primitives. Level sensitive, D latch, you have this. Purpose. Establishes transparency versus hold. Defines state retention under enable. 2. Edge triggered D flip-flop, master slave. Purpose. Defines cycle boundaries. Prevents time borrowing across stages. Is the unit of architectural state. This is mandatory. 3. Explicit clock phase generator or disciplined single clock. Purpose. Gives you a global temporal reference. Lets you reason about before and after. This can be a single step clock, or VH1, VH2, if you want stricter discipline. 4. State observability probe. Purpose. Exposes current state, write enable, and cycle index. Replaces the game's hidden test harness. Without this, debugging scales poorly. That's it. Anything else in phase 0 is optional enrichment, not a dependency. 4. Why SR latches are optional but acceptable. If you build them, do it for one reason only. To internalize that state equal to feedback plus delay plus exclusion. Once that clicks, stop. Do not let SR latches become a dependency of later components. They should never appear again after phase 0. 5. What you should not add before phase 1. Do not add T latches, JK flip-flops, gated clocks, asynchronous set reset variants, pulse generators. These complicate timing semantics and are actively hostile to composability in TC. Modern systems avoid them for the same reason. 6. Updated, mechanically correct phase 0 checklist. Your phase 0 should stabilize as SEPI code phase 0, time, state, and cause. If you have those four, phase 0 is complete. No missing primitives. No hidden requirements later. 7. Why this is enough for everything downstream. Every later structure is reducible to these. Registers, NDFF, plus write enable. Pipelines, registers, plus combinational logic. FSMs, registers plus decode. UO, registers plus tags plus arbitration. Caches, SRAM abstraction plus control FSM. NICs, DMA, queues, register files plus handshake. DSP, registers plus combinational math. ADC DAC models, sampling FFS plus math. Nothing else requires a new kind of state. 8. Recommendation, clear, final. Do not treat SR latches as a required milestone. Do build them once only if you want conceptual closure. Immediately proceed to master-slave D flip-flop. Clock plus probe. Then move to phase 1, pure combinational arithmetic. If you want, the next concrete step is to define a canonical register component, n-bit, write enable, debug ports. That becomes the backbone of phases 3 to 15. From a correctness standpoint, what you already have plus a master-slave FF is sufficient to build the entire system. Good. We'll do this cleanly and mechanically. You already have the only primitive you need. A level-sensitive D latch with enable. An edge-triggered D flip-flop is nothing more than two of those latches wired with complementary enables. There is no extra logic. I'll give you the exact structure. The dot graph you asked for. How to wire it in Turing complete. How to test it so you know it's correct. No abstraction gaps. 1. Definition, what you are building. Edge-triggered D flip-flop, master-slave. Inputs. D. LK. Output. Behavior. Q updates only on one clock edge. No combinational path from D to Q. We will implement a falling edge FF, common, simple. 2. Internal structure, non-negotiable. Master latch. Transparent when CLK equal to 1. Slave latch. Transparent when CLK equal to 0. Enable signals. And master equal to CLK. Enslave equal to CLK. Signal flow. Scopy coded, master, slave, Q. That's the entire design. 3. Dot graph, schematic you requested. This assumes your latch component is named the latch. Nginx copy edigraph. Nginx copy coded graph. DFF master slave. D. Latchum. CLK, latchman. CLK, no tone. Not one, latchin. Latchum, latch. Latch, Q. Expanded with explicit ports. Ruby copy coded graph. DFF master slave. D. Latchum D. This is exactly what you should build. 4. How to wire it in Turing. Complete, step by step. Place two instances of your level-sensitive latch. Name them master and slave. Connect. Master. Master. Slave. Slave. Q. Q. Clock wiring. K. Master. N. K. Not slave. N. No other gates. No feedback. No delay lines. No counters. If your latch is implemented via the 1-bit memory gate, this works perfectly. No special handling needed. 5. Why this produces edge-triggered behavior. Let's do the only analysis that matters. When CLK equal to 1, master is transparent. Slave is closed. Master tracks. D. Q does not change. When CLK transitions 1, 0, master closes. Slave opens. Slave captures master's last value. Q updates once. When CLK equal to 0, master is closed. Slave is transparent. Master is stable. Q remains stable. There is no time when D can directly influence Q. That is the definition of an edge-triggered FF. 6. How to test it. This is how you know it's correct. Do not guess. Do this exactly. Test protocol. Set CLK equal to 1. Toggle D repeatedly. Q must not change. Toggle KLK equal to 0. Q updates once. Toggle D while KLK equal to 0. Q must not change. Toggle KLK equal to 1. Q must not change. Toggle KLK equal to 0 again. Q updates again. If any of these violate expectations, the FF is wrong. 7. What not to add. Important. Do not add and gates on the clock. Gate the clock. Add extra memory. Add delay lines. Add counters. All of those break composability later. 8. Why this is sufficient for everything else. With this flip-flop, registers are trivial. Pipelines are trivial. Hazards are analyzable. Timing is explicit. Phase 1 arithmetic stays clean. This is the only state element you will ever need again. 9. Naming. Do this. Name the component something explicit, for example. DFF1 bytage. Later you will build DFFN bit, reg bitway, etc. All built from this. If you want next, the correct follow-up is build a canonical n-bit register with write enable and debug ports. That becomes the backbone of phase 3 onward. But first, build this FF and test it exactly as above.
What I don't understand is whether or not I should use a clock here or 2 inputs. Because the problem is that when you create a component on the component factory, it's meant to be used on the sandbox later, probably. So I can view, like if I put a clock here, I'm not really sure how it relates to the global clock of the sandbox. If there is a global clock on, I think that it has. The problem is that I never did any sandbox component, so I'm not really sure how it's gonna work, if I should use a clock or not on there. But I assume probably I will. But I'm not really sure if the game does that. But this is the biggest. I'm gonna ask that to GPT. It's basically saying to connect the clock on this latch, the enable here and not here. And the not goes to this one. So this one is here. Let me think. So this input goes to the M. And this one goes here. And this goes to the output. Yeah, it should be right now, based on what it's saying here. As enable. And the problem is that because if it is on here, not changing anything. Maybe this is wrong. Think on this. And the problem is that when the clock is on, it's also gonna be off here. It's not gonna change the state. Obviously, if I do this, then I'm not really sure if it's correct. This is not outputting anything. And now it is changing, but it's probably not correct. Yeah. Hmm. So from the way that I'm thinking about it, you should set whatever the value of D is, this input here, whenever the clock is high. I think that's how it's supposed to work. So probably this way it is correct. If I do this, can't. Yeah. But I think that this is how it's supposed to work, probably. So I'm not really sure. So I have an idea to make this easier. Just gonna export the circuit and share the code with GPT. Saving on the wrong path. Not sure if this makes sense. There are no knots here.
Good. This is a real confusion, and it comes from mixing two different clock semantics that Turing complete exposés. Once we separate them, everything snaps into place. I'll be very precise and concrete. 1. The root of the confusion, important. You are conflating. A clock signal is a value, a wire that is 0 or 1. A clocked memory primitive, TC byte memory, that already has edge semantics baked in. These are not the same abstraction level. When you use TC byte memory, you are no longer building raw latches. You are already using a clocked storage element. That changes what master-slave means. 2. Two different worlds, you must keep them separate. World A, gate-level latch world, what I was describing conceptually. In this world, there is no built-in clocked memory. Latches are transparent when n equal tune. Flip-flops are built from two latches plus inverted enables. This is where the NOT gate is mandatory. World B, Turing complete memory gate world, what you are actually in. In this world, TC bit memory already updates on clock edges. Save is a write enable, not transparency. You cannot recreate analog transparency. So, the master-slave construction must be adapted. Your instinct is correct that the earlier schematic as is does not map 1 to TC byte memory. That's not your mistake, it's a semantic mismatch. 3. What TC byte memory actually is. Let's be explicit. TC byte memory behaves like an edge-triggered register with write enable. Semantics, simplified. On clock edge. If save equal to 1, out, in. Else, out, out. This is already closer to a D flip-flop than a latch. So if you wire two of these in series, you are not building a master-slave latch pair in the classical sense. You are building two edge-triggered registers back-to-back. That distinction matters. 4. Why your circuit works but is not a master-slave FF. You proposed. First bit memory samples input. Second bit memory samples output of first. Both controlled by the same clock, enable. Yes, this will propagate input to output on a clock edge. But observe carefully. Both memories update on the same edge. There is no phase separation. No prevention of same cycle propagation. So what you have is effectively PGSQ. This is not a master-slave FF. It's just two registers in series, clocked together. In real hardware terms, this is a two-stage pipeline with zero cycle separation. 5. Why the NOT gate is required conceptually. The purpose of the NOT gate in a master-slave FF is not to block writes arbitrarily. Its purpose is this invariant. When the master is writable, the slave must be frozen. When the slave is writable, the master must be frozen. That mutual exclusion is what creates an edge. In gate-level logic. That's done with CLK. In Turing complete. You cannot do that with TC byte memory, because it has only one edge per cycle. So you must accept this. You cannot faithfully implement a true latch-based master-slave FF using TC byte memory. This is a simulator constraint, not a conceptual failure. 6. The correct conclusion. This is the key. You have two valid choices. Choice 1. Conceptual purity, harder. Build latches from gates plus delay lines. Use not gated enables. Build a real master-slave FF. Treat TC byte memory as forbidden. This matches theory perfectly, but fights the simulator. Choice 2. Pragmatic DC discipline, recommended. Accept TC byte memory as the primitive D flip-flop. Do not try to rebuild master-slave from it. Treat phase 0 as semantic anchoring, not literal transistor emulation. For your stated goal, system understanding and scaling, choice 2 is correct. 7. So what should phase 0 mean in Turing complete terms? Here is the corrected, simulator-aligned interpretation. 8. Answering your concrete questions directly. Should I use the clock gate or a normal 1-bit input? Use the clock gate, TC clock, only as the global clock. Do not treat clock as data. Isn't my circuit correct? It is functionally a register, yes. It is not a master-slave FF because TC already gives you edge triggering. Is the NOT gate wrong? In your TC implementation, yes, because you are already using clocked storage. In theoretical latch construction, no, it is essential. Both statements are true in different abstraction layers. 9. What you should do next, clear directive. Do not try to force classical master-slave latch theory onto TC byte memory. Instead, accept TC byte memory as your canonical. Define a standard register component. N bits. Write enable. Debug outputs. 10. Final grounding statement. What matters for the rest of your project is not, did I literally rebuild a master-slave FF? What matters is, do I have a state element with clean edge semantics and no same-cycle feedback? With TC byte memory, you do. That's the real bridge into phase 1 to 3.
Obviously, the reason why I used the 1-bit memory is because it told me that that's pretty much the same as the latch. But now it looks like it's not. It's saying that it's not. So I'm gonna try to see if I can build this thing here. But it should be easy. I just copy the schematics. The thing is, I don't know how to read this very well. Like this symbol here on the output. Don't know what it means. But obviously I can copy this, but I want to see with ChatGPT what it's gonna suggest when I go with the option 1 that it gave me there. I'm considering as well whether or not I should do this with Verilog instead of Turing Complete, and then just try to build the real thing instead of doing the simulator. But obviously Verilog is kind of worse because it's more abstract. So you're just gonna write the code and you're not gonna be able to visualize the connections. That's why I think that Turing Complete is probably better. Maybe I'll do both. I'll do Turing Complete first, then once I get to a level where I have a complex system, I convert into Verilog and then try to make it better there.
If you want conceptual purity, we need to be very explicit about what phase 0 is building and what it is not, otherwise you'll keep oscillating between is this a register, RAM, clock system. I'll answer in 4 tightly scoped sections. What phase 0 is actually for, and what artifact it must produce. Exactly which gates you will build, in what order. The concrete master-slave D flip-flop, gate by gate. How this artifact is used later, so it doesn't feel pointless. No shortcuts, no symbolic hand-waving. What phase 0 is actually building. Phase 0 is not building RAM. Phase 0 is not building a register file. Phase 0 is not building a clock system. Phase 0 builds the smallest possible stateful primitive with well-defined time semantics. That primitive is an edge-triggered 1-bit D flip-flop implemented from gates and delay with no hidden clocking. Everything else later reduces to arrays and control around this. If phase 0 succeeds, later phases never need to ask. When does state update? Can data erase itself? Is this combinational or sequential? That's the only goal. Second, the exact build order, no ambiguity. You will build 3 gates components in this order. Gate A, not gate. Already exists. Gate B, NAND gate. Already exists. Gate C, delay line. Already exists, this is critical. You will then assemble these into SR latch, NAND-based. Level-sensitive D latch, from SR latch. Master-slave, edge-triggered D flip-flop. You do not need NOR latches if you use NAND. Pick one family. NAND is standard. 3. Gate-level construction, this is the core. 3.1, NAND-based SR latch, first real state. Inputs. Active low set. RN, active low reset. Outputs. Q. Q bar. Gates used. NAND X2. Delay line X2, 1 on each feedback path. Wiring, explicit. Intercopy codec equal to NAND, SN, Q bar delayed. Q bar, equal to NAND, RN, Q delayed. Q delayed equal to delay, Q. Q bar delayed equal to delay, Q bar. Dot graph. Rust copy coded a graph. Sir latch NAND SN NAND Q bar NAND NAND 1 Q. Q delay 1 QD. RN NAND 2. QD NAND 2. NAND 2, Q bar. Q bar, delay. This is true beastable storage. The delay lines are not optional. 3.2 level sensitive D latch, from SR latch. Now we eliminate illegal states. Inputs. D. N. Outputs. Q. Q bar. Additional gates. NAND X2. Not X1. Logic. Any copy code is N equal to NAND, D, N. RN equal to NAND, not D, N. Feed SN and RN into the SR latch above. Dot graph, expanded. Rust copy coded a graph to latch D. D, NANDs. N, NANDs. NANDs SN. D, no tone, NANDR. N, NANDR. NANDR, RN. SN, SOCH. RN, SWatch. Slash Q. Slash, Kabar. Behavior. N equal to 1, transparent. On equal to 0, hold state. This is a real latch, not a register. 3.3 master-slave edge-triggered D flip-flop, the goal. Now we finally build time. Inputs. T. CLK. Outputs. Q. Internal components. Latch X, Zwite, not X1. Enables. Intercopy coding master equal to CLK. Enslave equal to not CLK. Wiring. Rust copy coded, master. Master. Slave. Slave. Q. This is a real master-slave flip-flop, built exactly as textbooks describe. No hidden clocks. No built-in memory. Only gates and delay. 4. About that 6 NAND positive edge DFF you found. Yes, that schematic is valid. What it is. A collapsed form of exactly what you just built. Master latch plus slave latch algebraically optimized. Still assumes propagation delay. What it is not. Simpler to reason about. Easier to debug in Turing complete. I recommend build the decomposed version first, SRD latch, FF. Later, you can optimize into the 6 NAND version as an exercise. If you start with the optimized version, you lose causal clarity. 5. Naming, important for later sanity. Use explicit names. Example. NAND. These names matter when you later inspect large systems. 6. How phase 0 artifacts are used later. This is where it stops feeling abstract. Phase 3, registers. A register equal to n copies of DF edgems. Write enable equal to gate D path. Phase 4, FSMs. State equal to vector of DF edgems. Phase 5, memory interfaces. Control state equal to flip-flops. Outstanding requests equal to Phase 7, UO. Rob entries equal to registers. Tags equal to registers. 7. Final grounding statement. You are not building RAM in phase 0. You are defining what it means for the universe to remember 1 bit across time. Once that is done faithfully, everything else is architecture, not metaphysics. Next correct step after this. Build a 1-bit DFF test harness, manual clock toggle plus probe. Then an n-bit register component from it. If you want, next we can. Verify your NAND SR latch wiring. Or translate your spreadsheet schematic exactly into Turing complete gates and check it for correctness. But now the target is precise and unambiguous.
So I think what it's saying is that I should build the SR latch first with NAND, then use this to build the master slave one. And I think that the first thing that it gave me there is the... I asked to not use these letters, but it didn't understand. Let's see if I can kind of try to understand what's going on here. I think the enable is going to be this one here, the top one. So go shoot two nuns. So this is the enable here. Then the D goes to not and R. I'm gonna assume this one is the R one. So I don't understand what it's saying by this RN here. Like, because it doesn't make sense to be on the same one, so I'm assuming this one should go here, maybe. Yeah, it doesn't make sense. I'm gonna ask to clarify what does it mean by this. I'll be right back.
Good. This is exactly the right objection. I was still speaking one abstraction layer too high. Let's drop all symbolic shorthand and talk only in concrete wires, concrete gate names, concrete directions, exactly as you asked. I will do this in 3 strictly separated steps, and I will be explicit about component factory boundaries. Big picture, before details, 1 paragraph only. Yes, you should build an SR latch first as its own component, using only NAND plus delay line. Then you build a D latch using that SR latch as a subcomponent. Then you build a master-slave edge-triggered D flip-flop using 2 D latches. This mirrors real hardware pedagogy and keeps the learning faithful and layered. Now we go gate by gate. Step 1. Build a NAND SR latch first component. This component has 2 inputs and 1 output. We will ignore the inverted output for now, to keep it simple and TC friendly. Component name. Ing copy codes or latch NAND. Inputs. Top input, N. Bottom input, D. Yes, this looks odd for an SR latch. I'll explain why this naming still works. Internal gates you will place. NANDA. NAND. Delay linear. Delay line ebb. Wiring, exact, no symbols. NANDA. Input 1, N. Input 2. Output of delay line ebb. Output, wire named wira. Delay linear. Input, wira. Output, wire named.
Let's see. Now it's saying that I shouldn't use the not. So then A inputs enable 1, with 2 delay line B. Not sure what it means by line B, but maybe it's directly here. So this is here. And B puts D1. 2 outputs of delay line A. This here. Not sure if I'm doing this correctly. Seems that it wants me to do this. And the pattern that I know is the one that does the toroidal thing, like this thing here. question is whether or not to use this one in here. Output of delay line B. So I don't think that's this should be like this, I think. Wire A. I think it's this one. Yeah, probably not correct. Or maybe it is, but it's just inverted there.
Named wire A delayed. Non B. Input 1, D. Input 2. Output of delay linea. Output, wire named wire B. Delay line ebb. Input, wire B. Output, wire named wire B delayed. Output. Output gate, output. Connected to wire A. What is happening plain language? NAND and NAND feed into each other. The delay lines break the instantaneous loop. The circuit stabilizes into one of two states. Changing in or D perturbs the loop and causes a new stable state. This is real beastable storage. No clocks. No memory primitives. Just feedback plus delay. How you test this component. Toggle N and D slowly. Observe that output. Sometimes changes. Sometimes holds. Most importantly, it remembers a value after you stop toggling inputs. If it does not remember, the latch is wrong. Step 2. Build a level-sensitive D latch, second component. Now we make the latch safe and usable. Component name. Nginx copy coded latch level. Inputs. Top input, N. Bottom input, D. Output. Output. Internal components used. NAND 1. NAND 2. One instance of /NAND from step 1. Wiring, exact. Not gate. Input, D. Output, not D. NAND 1. Input 1, D. Input 2, N. Output, wires. NAND 2. Input 1, not D. Input 2, N. Output, wire. /NAND. Top input, N, wires. Bottom input, D, wire. Output. Connect to output. What this guarantees. When N equal to 1, output follows D. When N equal to 0, output holds its last value. No illegal states. No.
So I'm gonna go again on the first one. And I have to check to see. I think I can kinda understand how to test to see if this is correct or not, but I'm gonna go over more times with HBT to try to understand if I'm building this correctly or not. Okay, so I assume NAND A is this one, the bottom. So the first input is the enable. Outputs of the delay line B. So I think what it's saying is that I should do this and then connect here. I think that's what this means. So delay line A is here. The input 2 is gonna be this here. Delay line B. Yeah, but this part is the one that I'm not really sure. I think it has to be direct, like directly here. That's probably the correct way to do it. But then how do I know if this is correct or not? Kinda weird because I guess I have to change here. Yeah. So I think. Yeah, so when this one is supposed to be the enable, I think. I confused the two, but I think the pattern is correct. Because I thought about the enable as this one. I think it makes more sense to think about the enable as the top one. So the top is the enable, and whenever the enable is on, it should update the value there, I think. Or maybe it's the other way around. Because I followed the instructions thinking about the enable as the bottom one. I'm not really sure if this is correct or not. So if you think about the enable as this one, then it is correct, I think. Or maybe not, because it's not setting now. So I'm not really sure. I'm gonna have to ask GPT.
States. No race.
I
This
think
is
it
a
is
real
not
level-sensitive
correct.
D-latch,
The
exactly as in
pattern seems
textbooks.
to be correct,
Test procedure. Set n equal to
obviously.
1. Toggle D. Output must
But
follow.
maybe
Set n equal to
shouldn't
0.
use the delay
Toggle
line.
D. Output must not change. Now we introduce time. Component name. Nginx
Not
copy
sure if
coded
it's gonna
fetch
change
triggered
anything.
master slave. Inputs. CLK. D. Output.
Something like this.
Output. Internal components. Latch level, master. Latch level, slave. Wiring, exact. Not. Input, CLK. Output, no to CLK. Master latch, latch
I
level.
got this when
N,
trying to solve
CLK.
one of the
D,
levels.
D. Output, master out. Slave latch level. N, no CLK. D, master out. Output, connect to output. What this does, mechanically. While CLK equal to 1, master is transparent. Slave is closed. When CLK switches 1, 0, master freezes. Slave opens and copies master. Result. Output changes only on the edge. This is a true edge-triggered D flip-flop, built entirely from gates and delay. Answers to your direct questions. Should I build SR latch as its own component? Yes, absolutely. That is the faithful correct way. Are we building RAM or registers here? Neither yet. We are building the atom of memory. Registers and RAM are arrays of this thing plus control. Should I also build the 6 NAND optimized DFF? Yes, but only after this works. That optimized version collapses the same structure,
This
hides
clearly
causality,
incorrect.
is great for learning after understanding. Why this is worth doing. Once you finish this, clock edge stops being mystical. Pipeline timing becomes obvious. Hazards make sense. TC's restrictions stop feeling arbitrary. Higher systems stop feeling abstract. You are literally reconstructing the causal substrate that everything else depends on. Next step, only one. Before moving on, build SR latch NAND. Verify it remembers. Then we refine or optimize. If you want, in the next message you can. Paste your SR latch wiring description. Or paste exported Verilog. And I'll check it line by line for correctness. You're doing this the right way.
What if I just did one of them? This. That doesn't seem to change anything.
Good. This failure mode is exactly what should happen if one key causal detail is wrong. Let's slow this down and collapse the problem to first principles, one gate at a time, exactly as you asked. I'll answer your direct questions first, then explain why your current wiring cannot work, and then give the minimal correction. Direct answers, no padding. Q. 1. Should the output of one NAND be directly connected to the output of the circuit? Yes. The circuit output must be the raw output of one NAND, not the delay line. Q2. Should the delay line ever drive the external output? No. Never. The delay line exists only to break instantaneous causality inside the feedback loop. It is not storage, and it is not the state. Q3. Why isn't it acting like an enable latch? Because what you built is currently a combinational loop stabilizer, not a bistable memory. You accidentally remove the asymmetry that creates memory. Now let's unpack this precisely. What an SR latch actually is, mechanism level. An SR latch is not two NANDs connected in a loop. That description is incomplete and misleading. An SR latch is two inverting elements where each output is allowed to dominate the other only when the opposing input is asserted. That domination condition is everything. If neither side can dominate, the system collapses to a fixed point or oscillation, which is what you're seeing. The specific mistake you made. From your description, you did this, conceptually. Java copy code NAND. Input 1 equal to input A. Input 2 equal to delayed output of NAND B. NAND B. Input 1 equal to input B. Input 2 equal to delayed output of NAND A. This looks symmetric and correct. But it is too symmetric. What goes wrong? When both inputs are inactive, neither NAND has authority. The delay lines merely postpone feedback. The system converges to a static value or noise. No input has priority over stored state. This is not memory, it's just a loop with latency. The missing ingredient, dominance. For a latch to store state, one input must be able to forcibly overwrite the loop, regardless of the previous value. That means, one NAND input must be unconditional. The other must be conditional on feedback. Right now, you made both conditional. Correct SR latch structure, NAND, concrete, TC friendly. We'll name everything explicitly and remove ambiguity. Gates used. NAND 1. NAND 2. Delay line 1. Delay line 2. Wiring.
This time I'm going to do the enable as the top. This is gonna be NAND 1 and enable here. Okay. Enable here. Put two outputs of delay line 2. What does it mean by that? Delay line 1 is gonna be this one here. Which way the best way to how this? Let's kill delay. Which one is I'm not sure if I understand because it's basically the same thing as the one before. I do like this, I think. This is NAND 1, puts 1, enable 1. Put true outputs of the delay line. Should be this one. I think that this is like what it's telling me to do, but it's probably not correct. Like it might be something to do with the game as well. Because on the level of saving gracefully, I tried to do this pattern and it doesn't work because of the NAND message that I got there. So I searched for the solution and I found the other one. There might be something related to the game, I think, but based on what it's saying here, I think that this should be the thing. And then the output would be this one probably. The raw. The ley line one. Yeah. Or maybe it's this one because it's the first one. So it's saying that the output should be this one, I think. But this is basically the same pattern that I had on the other one, so I don't think it's gonna work. Enable. Let's put the delay line true. U-bar delayed. Yeah. It's basically the same thing. Yeah, it doesn't work. Should set the output to 1, I think. Yeah, not sure.
This is the critical part. NAND 1. Input 1, N. Input 2. Why this version works. Let's reason causally, not symbolically. Case 1, N equal to 0. NAND 1 output is forced high, inactive. Feedback is broken. Output holds last stable value. No amount of detoggling can propagate. State is preserved. Case 2, N equal to 1. NAND 1 becomes sensitive to feedback. NAND 2 injects new information via D. The loop resolves to a new stable equilibrium. Delay lines prevent race collapse. State updates. This asymmetry is the entire latch. If both NANDs treat feedback equally, nothing can win. If one side has authority, memory exists. Why the delay line must not drive output? A delay line does not store, does not
We'll
stabilize.
go back to see the inputs on both cases. And one input should be enable, delay true. This one. Here should be input D, Q delay. Delay. That's confusing. Yeah, I think that it should be this one. Like based on the description, I think I did it correctly. But it doesn't get the result, I think. It's basically the exact same circuit I did.
Good. This failure mode is exactly what should happen if one. Why we stop here? You do.
Yeah, I'm gonna stop now because I've
tell you
been here for almost 2 hours. So I don't think I'm gonna do anything off stream. I might just continue to talk to ChatGPT to try to resolve this, or maybe like I'm probably gonna ask to see if I'm testing correctly, like check the truth table basically. So toggle the inputs and try to confirm. The problem is that you have the tick here, so it might be more complicated. But I want to try to see if I figure out if this is the correct one. I think I'm pretty confident that it's probably not, because the way that I think about it is that whenever this input here is on, which should be the enable, you should set the value of the output with the value of this input here. And obviously, oh, here it is working, but I think if I do this, yeah, it doesn't work. So there's something going on here. It might be because of the game though. That's the thing. And the thing that I thought about, like connecting direct here, I don't think is gonna work either. If I do this, or maybe this way works. But I think based on the description I was giving me there, it's either gave me the wrong description or there's something with the game that makes it not work for whatever reason. Yeah, here it doesn't work anymore. So I'm probably not gonna be able to figure this out upstream. Next time we're just gonna continue to, we're just gonna follow the list here of components and then just do everything on stream so that upstream we can focus on other stuff. Next time probably gonna continue from this place here, trying to figure out how to do this SR latch and build to the other components so I can build the more complex circuits eventually. So see you next time.